Okay, so it's asked to look at two questions in the lead case study, 5 and 9. So number 9 reads, when a metal such as lead is oxidized, and then that's described as losing electrons to form a positive cation, how does the solubility change? How does the solubility of a metal ion like lead affect its toxicity? So if we think about things, when we observe metals and objects made out of metals, such as lead pipes, well, there's a reason that we choose a metal for those jobs is because it's not going to wash away. So what you can say here is that lead metal, when the lead is not in a compound but is in its elemental form, is observed to be insoluble in water. And you can, if you want to extend this, you say this seems to be the case for many metals. Indeed, that's why we build things like bridges and cars out of metals. It would be no good if they were to wash away when it rained. Now, when metals form compounds, they form cations, right? They lose electrons. So we would expect that lead, when it forms compounds, is also going to lose electrons and form cations. And the question is how does this affect solubility? Well, if we relate this to other metals, if we think about something like salt, which is composed of sodium cations and chloride anions, salt dissolves well in water, doesn't it? Right? Salt dissolves well in water. Or if we think about something like sodium hydroxide, that also is often in many of the examples that we've seen a solution in water, an aqueous solution. And there are a few other examples like this. So metals, when they form ionic compounds, what we call salts sometimes, they are often water soluble. That's why the ocean is salty. It contains a bunch of these ionic compounds. So we can write many ionic compounds appear to be water soluble. So it's reasonable to expect that the solubility of metals appears to be greater when it forms cations. Because what we see is that when a metal is found in a compound, its solubility seems to be increased versus when it's in its elemental form. Now, how would you expect that to affect toxicity? Well, it can form a solution and get into all sorts of different parts in your body, can't it? So you could write something like this. I would anticipate this would mean water, or let's just say compounds of lead would be more toxic than lead metal as they are more likely to be water soluble. Now, if you do a bit of hunting around and you do a little bit of research, you'll see that some compounds of lead are not water soluble, but others are. So what we tend to see is that lead metal itself is very insoluble of water, but when the lead becomes oxidized, forms a cation, then in some cases it combines to form ionic compounds that are very soluble in water. And those solutions containing those lead ions can get to all sorts of different places in your body that solid lead never could get to. So it's a reasonable assumption to think that you really want to prevent the lead from reacting and forming these compounds that may just dissolve. So number 9 is a more numerical problem, and I can understand why you might have some difficulty with number 5 because it's sort of descriptive and you have to piece together what you observe in the real world to make some conclusions. Some real scientific reasoning going on there. All right, number 9, like I said, was a numerical problem. So it says, according to the EPA site, if greater than 10% of tap water samples exceed the action level of 15 parts per billion, remediation is required. So 15 ppb means that you have 15 micrograms of lead for every 1 kilogram of solution. Okay, so that's how much, that's what that means. Now it says a part per billion is parts per billion and is an indication of the mass of grams of lead per billion grams of water. So this is kind of an alternative way of writing ppb is micrograms per kilograms, but if you want to, you can you can write this as 15 grams of lead per billion grams of water. Okay, if you want to use that as your conversion factor, you could make it a little easier for you. All right, so it says convert 15 ppb to grams per mil. So the first thing I'm going to do is going to write this out using this conversion factor. And then I'm going to use this information here, which says that there is 1 gram of water for every 1 milliliter of water. And there we go. We have achieved our conversion. So put that into my calculator. Right. 15 divide 10 to the 9, and we don't really need to multiply that by 1 on 1, do we? And there we go, 1.5 by 10 to the minus 8. Grams in 1 milliliter. Just double check that. Yeah, so that's correct. There we go. Okay, Rose reads in one source that lead concentrations are generally below 5 micrograms per milliliter. How does this compare to the 15 ppm? So clearly that should be ppb, so we should correct that. But you can compare it to 15 ppm if you want to. So we need to turn 5 micrograms per milliliter into grams per milliliter and then compare it with this value. So 5, and instead of writing the symbol micro, we can just write that as 5 by 10 to the minus 6 grams per 1 milliliter. Because remember that micro just means times 10 to the minus 6. So that we're going to compare with what we just calculated before, 1.5 by 10 to the minus 8 grams per milliliter, and you can see it's many times bigger, isn't it? Now, if you wanted to get fancy, we could go, well, 5 by 10 to the minus 6 grams per milliliter divided 1.5 by 10 to the minus 8 grams per milliliter, what does that equal? So let's just do that. 5 by 10 to the minus 6 divide 1.5 by 10 to the minus 8. And what are we going to see? It's 333 times bigger. All right. So this ends up being 333 times larger than what they call the action level when you have to do something about cleaning it up. Okay, so that's it. So yeah, the first question there, we're just kind of using some logic to think about how the solubility of metals is different when we have the pure metal versus metals in compounds, which is really applying general knowledge there. And so when we think about that and we apply it to lead, specifically, one comes to the conclusion that it is reasonable to think that if the lead is dissolved in the form of cations, then it would be more toxic than if it was undissolved in the form of a solid lead pipe. All right, in the second one, what do? We use the definition of parts per billion given to convert the number given to grams per milliliter, and to do that, we're going to use the density of the water. Once we've got that, then we compare it to the 5 micrograms per milliliter concentration that's observed, and to convert that value to grams per milliliter so we can make a direct comparison, we noted that the symbol micro is just exactly the same as times 10 to the minus 6. So I then got fancy and took the observed value and divided that by the standard value where we have to take action and treat the water, and I realized that the observed value was 330 times bigger than that action level. So anyway, I hope that's helpful, and good luck with everything.